with Soda Labs. We've heard about TE, we've heard about ZK, we've heard about FHE, and Avishay is going to talk about Garbled Circuits. Thank you very much indeed. Thank you.
Is there a pointer? Okay. So hi everyone, I'm Avishay Yanai. I'm gonna speak about Garbled Circuits and the GC EVM. So we all know what is the problem of confidentiality in the blockchain. Everything is open. Once you do a transaction to the grocery store, the owner can track everything you do on chain. There are many applications for that can benefit blockchains and the efficiency of blockchains, but they cannot actually go and onboard because of privacy issues. Think about your business and how do you pay your employees? How do you pay your service providers? How do you manage portfolios and ownership structures? How do you do governance, elections, polls? How do you make DeFi fair? And finally, how do you play games with partial knowledge? All of these applications, they require privacy on chain. So we gain transparency from blockchains, but we must have some aspect of opaqueness that hides actions that we do, not because we do bad actions, but because those actions are private. They are sensitive information for us and for our business. Therefore, we must have both transparency and privacy. So GC EVM, GC is for Garbled Circuits. EVM is because it's an extension for EVM. It's a fork of Go Ethereum. It's MPC-backed EVM extension that basically adds new instructions or actually pre-compiled contracts that whenever they are triggered, they trigger an MPC network to do some operations. So how users and developers interact with such an object. So for users, whenever they want to come and send ciphertext to the network, they will need first to onboard, meaning to ask the network to generate an encryption key for them. So the network has an encryption key per user. This is a symmetric key, and this is why it's per user. Each user has its own symmetric key, and whenever it wants to give some sensitive data to the network, it first encrypts that data using its own symmetric encryption key. And in addition, the network also has a global network key, which is also a symmetric key. And when a contract wants to store something for a later use in an encrypted manner, it uses its own global encryption key to do so. Developers, they can simply migrate contracts from Ethereum to this layer 1. Everything will work just fine, but without privacy. In order to add privacy, they need to adjust some of the operations in their contract so that instead of using regular opcodes like addition and multiplication, they will use the secure addition and secure multiplication. If you are familiar with FHE EVM, then this is quite similar to those operations, secure operations, except here the backend technology is much different. Yes. It's not working? Yeah, okay, so to see how transactions are going through inside the GC EVM, think about the user who has an AES key. This is the user key, and the user wants to give some ciphertext to the network. And inside the transaction, the user will input, will give some arguments. Some of them are called input text, and some of them are called plain text, just simple values. And input text are a special form of ciphertext. They are a ciphertext using AES key, as well as a signature on some metadata, like the message sender, the contract address, the method signature, and so on. And we add this signature on this metadata because we want to make sure nobody will be able to steal that ciphertext from that user. So think of an encryption that you send to the network. And then if you send it to an auction contract, and then I see that you sent a ciphertext to an auction contract, and I want to compete with you, I can just simply steal your ciphertext and send the same ciphertext, right? And then we'll compete and send the same value. But there are two mitigations here. One of them is that we use symmetric key encryption. And then when the network decrypts that value, it will decrypt it with a different symmetric key. It will decrypt your ciphertext with your symmetric key, but my ciphertext with my symmetric key. And therefore, the values, the output values will be different. And second, you signed on that ciphertext, and therefore I cannot take it and send it again because I don't have the contract checks to which contract and method it was signed. Therefore, this mitigates the attack on ciphertext theft. So the validation that I mentioned is happening here, just at the arrival of the GC EVM execution layer. If it passes the validation, it's going through a decryption and gets into a ciphertext, special form of ciphertext called garbled text. And this garbled text is a special form of ciphertext that is that we can do operations on it. So even though it's encrypted, we can still do operations like addition, multiplication, division, whatever you want, on those garbled text. So in this box, which we call garbled execution environment, we can do whatever operations we want on that special form of ciphertext. And when we get the output, which is also a form of a garbled text, we encrypt it back either to the user, which will receive that encryption as a receipt, or to the network, which will store that ciphertext to the contract state. So everything is flexible. You can encrypt every value to whoever user you want, or to the network. So this is an example of a confidential ERC20 contract that runs on the network. So in this transfer function, you can see the input text, which are ciphertext and signature. Here, this input text is validated. And if it's validated, the result of this thing will be a garbled text. Now, that garbled text will enter into a contract transfer. It's another function that will actually change the balances of the sender and receiver based on the amount that was sent in this CTU in 64. It's just an amount of 64 bits. Yes. And finally, look here, there is a Boolean value that was sent by the sender of this transaction. If this Boolean value is true, then it means that the contract needs to decrypt the result of the transfer to everyone. But the user can decide whether it wants to decrypt that successful result to everyone, or keep it private between him and the receiver. This is the overall view of the GC EVM network. We know that we must separate between sequencers and executors. And this is true for every MPC-based chain. I'm not sure it's true for TEE-based chains, but we can talk about it later. But for every MPC-based chain, this is true because of a simple reason that the sequencers, they cannot finalize blocks. Why sequencers cannot finalize blocks? Because when they get transactions, in order to finalize those transactions, they need to execute them. And to execute them, they need to run, if they contain ciphertext, they need to run some MPC protocol. And when they run MPC protocols, they are getting into a zone that is dangerous because MPC protocol might decrypt some of the values. So if they decrypt some of the values before the transaction is finalized, there might be a privacy leak, right? Therefore, we get to the chicken and egg problem, and we must separate between sequencers and executors. Questions about that? So, yeah. Yeah, you can. So right now, actually this week, there will be a launch, testnet launch of the network with the Coating Network, which is also a sponsor of this event. This will be the first fully fledged EVM compatible MPC supported chain. Probably in addition to Zama, I'm not sure if the decryption key is shared already or not. But anyway, it is already supported by 3 wallets, and it's very easy to support by wallets because we only use symmetric key encryption and basically Web 2 cryptography. So everything is quite easy. The encryption is AES 128 counter mode, and we use for key encapsulation mechanism RSA. Right now, we can manage about 50 confidential ERC20 transactions per second. This is just the contract that I showed you before. With pre-execution soldering that I will explain a bit later, we can reach about 1,000 TPS of confidential transactions. For non-confidential transactions, the numbers may be much larger. And this runs on normal AWS M5 large machines. And right now we're experimenting on much weaker machines. Those are already weak machines, but we are experimenting on much weaker machines. And it runs just fine. We don't need special hardware or anything. Bandwidth per confidential ERC20 is about 1 megabyte. And if you calculate the monetary cost of this, you get something very close to 0, which is going to reduce even more. So I told you about GCVM, but I didn't tell you anything about garbled circuits. So what are garbled circuits? This is a very simple illustration of garbled gate, actually, of an AND gate. It's just for illustration and not secure. So an AND gate has 2 input wires, A and B, and 1 output wire, C. To garble the gate, I will assign 2 cryptographic keys, encryption keys, A0 and A1, to wire A, and so for B and C. A1 and A0 and A1 will represent values 0 and 1 respectively. And in addition, I will generate 4 ciphertext in the 4 rows below that they will represent the garbled gate. So the idea is that if I give you the key A0 and B0, you will go to the first row here and decrypt that value. And after you decrypt that value, you will get the value C0. And C0 represents the value 0. That actually is the function on the end on 0 and 0. So it actually computed the function correctly. Of course, it's not secure because now I told you that I gave you the keys of A0 and B0, so you know that the values on the input wires are 0. So there are ways to protect against this privacy issue, and I'm not going to get into this right now. What I want to, you can. What I want to stress is that garbled circuits are a cryptographic object that represent an encryption of a function, not just an encryption of some value, but an encryption of a function. And in order to evaluate that function securely, the evaluator needs to have 1 cryptographic key on each of the input wires. And this way it gets 1 cryptographic key at the output wire, and then it can continue evaluating more and more gates until the end. And in the end, it can decode from the cryptographic key that it got to the value that it represents, to the actual Boolean value that it represents. Yes. So from garbled circuits to two-party computation, this is basically the YAO protocol. It's quite famous. In that protocol, we have a garbler and evaluator. The garbler generates all the garbled gates, and here we have special function called oblivious linear evaluation. We'll show you soon what it does. And after the garbler generates all those keys, 2 keys per input wire, and 2 keys for the output wire, and some decoding information, it sends the garbled circuit, this one, to the evaluator. And in addition, it sends 2 keys for the first input wires, because the garbler is the one who has the input bits to those wires. So the garbler is the one who knows alpha and beta. So it knows which keys represents alpha and beta. And the evaluator, it has the value gamma on this wire, and it needs to obtain that key that represents gamma. So it does this using a sub-protocol called oblivious transfer between the garbler and the evaluator that hides from the garbler which key actually the evaluator selected. Using those 3 keys, as I mentioned before, the evaluator can compute the garbled circuit that actually computes this function. So y delta is the key that will be obtained by the evaluator, where delta equals a XOR b and gamma. It doesn't actually matter. And using this decoding information given by the garbler in the first place, the evaluator can decode from y delta to the actual result of the function delta. So this is the high-level structure of garbling-based protocol. Now, yeah, another one, please. Yeah, so there are 3 actually aspects in which we take this idea and bring it into blockchains. So first thing, of course, you may say is how to make it work on more than 2 parties, right? Then the first thing that we do is to make it work on multi-party, and there are many papers in the literatures that try to do this, but they are called multi-party garbling, and they are all have a bad effect on the performance and the size of the garbled gates. So before I showed you a garbled AND gate with 4 rows, and when we move to multi-party garbling, the size, the number of rows, it grows with the number of parties. So if we have three parties, it will be 4 times 3, and if we have n parties, it will be 4 times n. In addition, the performance decreases with linearly with the number of parties. So those protocols of multi-party garblings are not fit very much to blockchains. What we do instead is distribute. We take the 2-party protocol that I mentioned, and we separate the roles of the garblers and the evaluators, and distribute them individually, separately from each other. And then the garblers in the offline, they generate a lot of garbled circuits. They spit it out to the network of evaluators, and in real time, when there are transactions that involve secrets, the evaluators can stitch together small garbled circuits and do the actual computation. So this is actually mentioned here. That technique is called soldering, and this actually allows us to have the garblers generate a lot of small garbled circuits for each opcode of the EVM, and then in real time, when there are transactions, the evaluators can stitch together small garbled circuits. For example, here they stitch together small garbled circuits to represent a big transfer transaction. So this is exactly how it works. And in addition, using garbled circuits allows us to obtain public verifiability or auditability, which is a very important feature of MPC. It means basically that we have observers. They are not part of the computation. And even though the entire MPC network may collude, this is a big problem, the observers can make sure that the MPC do the work correctly without cheating. So even though the MPC network may collude completely and try to cheat, they will not be able to steal your funds. This is basically the premise. And with that feature, we can go to beyond layer 1 and go to rollups. I will not explain everything here. I'll just mention to people who know how rollups or how interactive fraud-proof rollups works. So there is that bisection protocol in which the guy who sent the attestation and the guy who sent the dispute, the protocol make them agree on the exact opcode where they disagree, actually. And then on that specific opcode, the contract will run. The contract on Ethereum will run that opcode and check who actually stated the result correctly and decide who to slash and who is correct. So we took the same idea and we do a bisection over a garbled circuit in order to get to the specific garbled gate, a specific gate which is a very like the atomic operation and or XOR and so on, where the guy who sent the attestation and the guy who sent the dispute are disagreeing, and only that atomic gate will be executed by layer 1 Ethereum. So yes, with that I will finish, and thank you for your attention.